In today's world, information is everywhere, but not all of it is reliable. From smart devices to autonomous vehicles, from disaster response systems to mobile recommendation engines, we're constantly bombarded with data. The real challenge isn't gathering information, it's making sense of it, especially when that information is uncertain, incomplete, or contradictory. This is where information fusion comes in, the process of combining data from multiple sources to generate more accurate, meaningful insights than any single source could provide alone. Traditionally, this was done through rigid hierarchical systems, think military command structures, where orders flow top-down, and every piece of data must be routed through a central node. But that model doesn't scale well in real-world environments. In dynamic, decentralized systems, like mobile networks, sensor arrays, or peer-to-peer P2P systems, centralized control breaks down. Devices fail. Batteries die. Connections drop. Communication is limited by bandwidth, latency, or energy. So what happens when you can't rely on a central authority? The answer lies in holonic structures, self-organizing, adaptive systems composed of semi-autonomous units called holons. Each holon behaves both as a whole and as part of a greater whole, like a cell in a body, or a team within a company. This isn't just theoretical. It's emerging naturally in systems where resources are constrained, where every message costs energy, every query consumes time, and every failed transmission reduces trust. Let's dive into how this works. What is a holon? The term was coined by philosopher Arthur Koestler in The Ghost in the Machine, 1967. A holon is an entity that is simultaneously a whole and a part. It can operate independently, but also collaborate with others to form larger, more capable systems. In technical terms, a holon is semi-autonomous, it makes its own decisions. Hierarchically embedded, it can be a component of a higher-level holon. Recursively self-similar, the same structural principles apply at every scale, from a single agent to a network of agents. Goal-driven, it acts to achieve collective objectives, not just individual ones. These properties make holons incredibly resilient. When one component fails, the system doesn't collapse, it adapts. Why holons over hierarchies? Traditional hierarchies are efficient in stable environments. But they're brittle under pressure. If the top node fails, the whole chain breaks. They're also inefficient. Every piece of information must pass through multiple layers, increasing latency and data loss. Hierarchies, dynamic, flexible, self-organizing structures, solve these problems. They distribute control, reduce communication overhead, and adapt to changing conditions. And crucially, they emerge naturally when you constrain communication. The model, a self-organizing multi-agent system. Imagine a network of agents, software entities, sensors, or smart devices, all trying to answer a question. Is this car suitable for purchase? The answer depends on multiple attributes: price, comfort rating, number of doors, air conditioning, fuel efficiency, etc. Each agent has partial knowledge. Some know about price, others about comfort. But none have the full picture, and each has limited resources, a finite number of messages they can send, a short battery life, or a tight deadline. Here's how the system works. Phase 0: training. Agents learn how to estimate the value of each attribute based on their own data. They develop prediction models and calculate error rates, how confident they are in their own answers. Phase 1: exploration. The system starts in an unrestricted mode. An agent queries all other agents about each field. It records which responses were most accurate, which agents consistently gave the lowest error. Phase 2: intelligent operation. Once the agent identifies its favorite peers, those that deliver the highest quality responses, it switches to intelligent mode. It only queries these trusted agents. Why? Because sending messages costs energy. And when resources are low, efficiency becomes survival. But here's the key: this isn't random. It's driven by optimization. The system seeks to minimize uncertainty, to reduce indeterminacy in the final answer, while using as few messages as possible. And this is where holons begin to form. Let's say Agent Omega wants to know whether a car is comfortable. It queries 3 agents, Alpha, Beta, and Gamma. Alpha gives the best answer for comfort. Beta is best for price. Gamma excels at predicting fuel efficiency. Now, instead of querying everyone every time, Omega starts sending its queries only to Alpha, Beta, and Gamma, its trusted collaborators. But now Alpha, Beta, and Gamma don't just act independently. They start coordinating. Suppose Alpha realizes it can't answer a complex query about fuel efficiency, but Gamma can. So Alpha forwards the query to Gamma. And Gamma, in turn, might need data from Beta to complete its task. Now we see a pattern: a head-body structure emerges. Alpha becomes the head, the interface to the outside world. Beta and Gamma become the body, processing internal tasks. Communication flows through the head. This is the classic head-body holon architecture, first formalized by Fisher et al. But it's not just one holon. Multiple holons can exist simultaneously, even overlapping. An agent can be part of several holons at once, depending on the query. And here's the surprising part: this structure forms without any central design. It's not programmed. It's self-organized. The mathematics of emergence. Why do holons dominate in resource-constrained systems? Because they minimize communication overhead and maximize information quality. Let's look at the math. Suppose there are n agents in the system. Each agent can only send a limited number of messages, say 10. When an agent wants to query a field, it only sends to its top k trusted peers, say k equals 5. Now consider the probability that two agents, alpha and beta, communicate outside the head-body structure. That is, they bypass the holon head and talk directly. That probability is p approximately 1/n3, k minus 3. For n equals 20 agents, k equals 5, this becomes roughly 1 in 1042. That's not just low, it's effectively 0. So as the system grows, the chance of a non-holonic structure persists becomes vanishingly small. In the limit, as n right arrow infinity, the probability that any structure formed is a holon approaches 1. This isn't coincidence. It's inevitable under resource constraints. Real-world implications. This isn't just academic. This model has real applications. Wireless sensor networks. Sensors in a forest fire detection system must share data with limited battery life. Holons allow them to form temporary coalitions. A head sensor gathers data from a body of others, then collapses when power runs low. Vehicular ad hoc networks, VANETs. Cars communicate to warn of accidents or traffic jams. In high-density traffic, communication is chaotic. Holons let vehicles form temporary clusters. A lead car becomes the head, others relay data, reducing congestion and improving response time. Mobile recommender systems. Your phone could form a temporary holon with nearby phones to recommend a restaurant. It queries only the best local sources, saving battery, improving accuracy. Big data analytics. In distributed data processing, each agent specializes in a subset of data. Holons allow them to collaborate efficiently. One agent acts as the coordinator, others as processors, without constant coordination overhead. The power of self-organization. What makes this system truly powerful is its autonomy. Agents make decisions based on local information. They adapt dynamically when peers fail or messages are delayed. They use simulated annealing-style randomness, sometimes responding even if their quality is low, to avoid getting stuck in local minima. They learn from experience, updating their favorite lists based on past performance. And crucially, no central authority is needed. There's no server, no configuration file, no fixed topology. The structure evolves in real time, like an ecosystem. Challenges and future work. Of course, there are open questions. Should agents receive feedback on whether their responses were useful? Yes, but it adds cost. It's a trade-off between accuracy and efficiency. Can we design agents with different temperaments? Some could be nervous, quick to switch modes, others calm, more patient. This could improve resilience. What if agents disagree on how to decompose a complex query? That's a deep problem in ontology alignment. But if all agents share a common model, a shared understanding of what comfort means, the system works better. And finally, how do we verify that a holon is truly emergent? Not just a static cluster, but a dynamic, goal-driven, self-optimizing structure. This is where game theory and cooperative coalition models come in. When agents form a holon, it's not just convenience, it's mutual benefit. The expected utility of collaboration exceeds the sum of individual gains. This is the essence of self-organization, not chaos but intelligent emergence. Conclusion. In resource-constrained environments, where energy, bandwidth, and time are limited, rigid hierarchies fail. But holons thrive. They emerge naturally when agents optimize for information quality under constraints. They are adaptive, robust, efficient, and scalable. This is the future of decentralized intelligence. Not a top-down command structure, not a centralized cloud, but a network of semi-autonomous agents, self-organizing into holons, working together without coordination to make sense of a noisy, uncertain world. And as we move toward edge computing, IoT, autonomous systems, and real-time decision-making, this model isn't just useful, it's essential. Because in a world of limited resources, the most intelligent system isn't the one with the most power. It's the one that knows when to stop talking and start collaborating.